So we are now 62. Okay, good, a good number, 70. I don't know, getting more. I'm just reading the number of participants. Just reaching over 100 now. Let's wait a second. This is a very important seminar, so I'm happy to see that there are people, so many people coming, so 140. Okay, so today's webinar is on a very important topic about learning data, learning from data and integrating into the traditional data assimilation systems or less traditional. But before we go there, with our exceptional teacher, Rossella Arcucci, from Imperial College, I'd like to remind you of our CMCC. So CMCC is a foundation that tries to investigate in the best way the climate system, its interaction with society, and looking for reliable predictions or projections or simulations. So everything that is connected also not only to collection of real world data, but also the virtual world, the simulation world. So CMCC is organized into 7 separate divisions. Actually, no, the divisions are more, 9, but in 7 locations in Europe, in Italy. And you see quite well spread over the national territory. We're very proud of that. And then the research divisions are 9. And here, this talk comes mainly from the ocean prediction application and ocean modeling data simulation division, but is of interest for climate simulations, the prediction for everybody else, and advanced scientific computing, I guess. So the topics span from social sciences, social-political sciences, economy, to earth sciences, and also this is a very important spatial aspect of our work, which brings us together to try to solve the challenges of sustainable development goals, disaster risk reduction, and so on. So we have also a very good office for communication. Okay, as you know, because they organize the webinars, we have publications, and we have also a starting educational sector. Certainly high education is something that CMCC has always sponsored with PhD programs, but going now on the younger. Okay, so questions and answer session. Your audio and video is deactivated, so please use a raise hand and write in the question and answer section. I will read then your question, and I will ask Rossella to answer after her talk. So the webinar will be recorded, and since some of you asked me already, and they will be at the user place on the CMCC webinar. So to conclude, let me introduce you briefly Dr. Rossella Arcucci. She is a PhD degree from Naples University in mathematics, and now she is a research fellow at the Faculty of Engineering, Department of Computing of Imperial College in London. And her great background and work is connected to the frontier in data assimilation. But let's have her talk to us directly. And please, Rossella, the floor is yours.
Thank you very much. So let me share the screen. Can you see my screen?
Yes, we can.
Okay, perfect. So thank you very much for inviting me to give this talk today. And yeah, as Nadia was saying, I'm a research fellow at the Data Science Institute, Imperial College London. I'm the head of the Data Learning Working Group. And I'm basically a mathematician, let's say a computational scientist, but I will talk today about data learning, integrated data assimilation, and machine learning. So as you can imagine, there is a lot of math behind that. But I will not focus on the math, so don't worry, not too boring today. I will mostly focus on the methodologies, so on the technologies, the models, and how we integrate data assimilation and machine learning in these models that we call data learning models. So just to let you understand, when I will mention data in the future slides, what I'm talking about. So for us, data are several sources of data. First of all, we operate a lot with other scientists working on fields. So they have models, computational fluidodynamic models, for example. So they produce these simulations, and we have data from their simulations. So we are talking about data completely unstructured, for example, with mesh completely unstructured, and verifying reads, so very high resolution models, data from coupled models, so even more data, and obviously observations, as you can imagine, which is the standard way to imagine data. So from satellites, from sensors, and from a lot of different applications. In this slide, actually, the observations are from cryptocurrency, because the models we are developing in my group are not just applied to geoscience or air pollution, ocean, weather, etc., but also to other different applications. So how we face these problems? So we have all this data, and then we try to build data-driven models. This was the first main point when you have data, no? But unfortunately, as you can imagine, when you try to build a data-driven model for real-world scenarios, it starts to be quite challenging because of a few reasons. One of the first reasons is because all the data I was showing you, a lot of different sources, start to be quite a lot. So the matrices that we use to train our data-driven models start to be quite big. So we have all these dimensionality constraints, and this is the first challenge. The second one is the uncertainty. Obviously, when you build a model completely data-driven, you train information from the data, but you also train information on the errors in the data. So actually, you are learning everything. This is the reason why sometimes, if you don't develop properly these data-driven models, the error propagation explodes quite easily. Third point is low quality data. So when you have equations, for example, we work also with physical models, Navier-Stokes equation, etc. You can balance your variables somehow, but when you just have data, sometimes you have low quality data. With low quality data, we mean that sometimes you have data from one variable instead of another, for example, pressure or temperature. And this means that you have link to the variables interested in your field, but you don't have direct information about that variable. So for all these reasons, we couple these data-driven models with data assimilation. We say data assimilation is our missing piece. I will show you in the slides, in the following slides, what I mean more in details. This is just to show you the idea behind the models we develop. So, and the reason why we couple data assimilation technologies, data assimilation models with machine learning, with data-driven models. Another important part is that, especially when you talk with operational centers, and we are now today at the Mediterranean Center of Climate Change, for operational centers, data-driven models are like sometimes not acceptable because they are black boxes. So in the context of explainable AI, explainable artificial intelligence, we are using data assimilation to open this black box and give, let's say, an explanation of the weights of a machine learning model. I will give not too many details about this during this presentation, but if you're interested, we have few informations about that for the following. So as I was saying, then all the time we have to face these uncertainty quantifications problem and uncertainty minimization problems. So this is the reason why we couple data assimilation with machine learning in these data learning models. So this is what data learning means for our group. This is the reason why 3 years ago, I created this group at Data Science Institute. I will show you a bit more. So I'm quite sure that most of you already know what is data assimilation, but for the few people that are not aware of that yet, so data assimilation, as I told you, no math, but data assimilation is a model, is a technology that helps you to ingest in a computational fluidodynamic model, in a simulation, information, external information from observation. This is an example for about air pollution in a busy junction in South London. And we have data from sensors. So data assimilation is able to integrate this information from the sensors in a computational fluidodynamic simulation in order to have a better prediction, in order to improve the accuracy of the prediction. Obviously, as you can imagine, this kind of technology is very powerful. However, if you really want to have benefit from these technology, you have to face a few points. The first one is about efficiency, because if you integrate data from sensors in a CFD taking days of running, it's useless. So this is the reason why one of the main points is pushing on the improvement of the efficiency. Second point, accuracy. Obviously, if you want to integrate new information in a system that you already have, you want to be sure that you are maintaining a good accuracy. You are not introducing extra error in the system. Third point, obviously, if you want to apply that in real case scenarios, so you have to face big data problems. And the fourth point that I will mention just at the end of this presentation is about good quality data. So sometimes we, especially now that we have a lot of data from a lot of different sources, it sometimes is not really useful to assimilate all the data you have, but there are some technologies based on machine learning for optimal data selection that we use also for optimal sensor placement. And it can be used for any kind of real world application. I will show you a bit in the following. So data assimilation over the past year have been like really increased in sophistication. So there are really good data assimilation software worldwide used for mainly customized for the application. They are really stable now and really good. However, there are still few points that data assimilation we are trying to face. One is about the nonlinearities. So one of my main questions over the past 3-4 years have been, how can we introduce and how can we have benefit from artificial neural networks, for example, from machine learning to face these problems with nonlinearities in the data assimilation process. Second point, the background error covariance matrix. I'm sure that the one of you which is working with data assimilation know exactly what I'm talking about. So the background error covariance matrices are usually quite big, unstable, ill-conditioned, rank deficient. So all these problems, how we can face, how we can try to face the problems we have with background error covariance matrices using, for example, encoder-decoder technologies. I will show you what we have done about that. That point, sometimes, especially in 4-dimensional data simulation systems, so I'm talking about, for example, a 4D bar, or for example, extended Kalman filter, or other kind of hybrid data simulation systems, you have this point that then when you couple with the CFD, as the CFD, your model is computationally quite expensive, it is like affecting the efficiency of the whole data simulation process. This is the reason why we work a lot with surrogate models and with what we call reduced order models. And on the past year and a half, we started introducing surrogate models and reduced order models using generative adversarial networks, which are a kind of networks usually used for facial recognition. So, as I was saying, in order to face all these kind of problems, 3-4 years ago, I created in the Data Science Institute this group, which is growing quite exponentially now. We have an open position now for a postdoc. In case you are interested, you can check on the webpage of the Data Science Institute. And we apply this kind of technologies, data simulation and machine learning, to a lot of different real-world applications. So not just geoscience, but also social science, medical application, finance, robots, etc. And we do that in the context of few grants and collaborating with a lot of other different universities in UK and in Europe. So these are the main questions we are trying, usually we try to answer when we work on this kind of methodologies. So we want to focus on the predictions. So we try to improve predictions, and we try to accelerate the predictions, especially for decision making. You have to decide like almost in real time. And in these slides, I will focus about the how to achieve both accuracy and efficiency. And to do that, we focus on 4 main, let's say, kind of models. So the first one, in order to improve accuracy and let's say, cleaning the data, we develop methodologies about optimal data selection and also parameters estimation. For parameters estimation, I mean the use of data-driven models, also data simulation models, to estimate parameters that in your system are quite unstable. So in order to improve the values of the parameters, you can use this kind of technologies. For the efficiency, as I was saying, surrogate models, data-driven models. For the online, so when you are running then your system, you can use data simulation to improve the accuracy, and data learning, then the integration of data simulation with machine learning to also have a more efficient result. So as I told you, we are working on a lot of different applications, but in the following, just to fix one application, I will show you about these models apply to air pollution problems. So the models behind are Navier-Stokes models. This is like a snapshot of the campus of Imperial College. As you can see, on north there is Hyde Park, and then there is the campus, and all around there are a few museums, natural history museums and others. On the right hand side, there is the computational fluidodynamic result developed by the computational fluidodynamic group using this software called Arcucci. And we also have sensors all around the campus. So let's go deep in the details. So when you talk about data simulation, this is like a standard algorithm for data simulation. So the main problem is trying to minimize this cost function. Then there are a few ways to do that. If you solve that as a variational problem, then you have variational data simulation. If you fix the time, you have 3D bar. If you have a window of time steps, you have a 4D bar. If you solve this optimization problem using normal equations, you have Kalman filter. etc., etc. So the general way to represent a data assimilation problem is with the equation in line 6, where you just want to solve this optimization problem. You want to minimize this cost function. So the most popular approaches to introduce machine learning in a data assimilation process is mostly focusing on the, as I was saying, surrogate models, so M, and facing problems related to the background error covariance matrix B. And I will show you in the following few slides about that. So this is how we, for example, for air pollution, as I was saying. So on the bottom, we have the forecasting provided by the fluidodynamic software Fluidity. And this is for a fixed time step. And also we have the reconstructions from sensors of the observation. So the sensor is saying that actually the flow, the tracers are not going so towards, you know, one of the buildings, but they are exactly in the middle. It's not a lot about the spread, but imagine the direction is wrong. So with data assimilation, we merge this information in these, and we have on the right-hand side these results. You have to consider that this is done on completely unstructured meshes. So this is one of the main challenging for data assimilation, but I don't want to focus on that now. What I want to say is that to obtain these results, we had developed like a quite standard data assimilation approach, a 3D VAR in a control space. So this is very standard. This was like the beginning, like 4 years ago. 4 or 5 years ago. So we have like these, in this assimilation, so in this technology, there is the minimization of this cost function. We have good results, okay. However, as I was saying, we are losing, because of the truncation singular value decomposition, we are losing a lot of information about the data because we are introducing linearities. So if you don't want to have that, but you want to keep more non-linearities in when you reduce the space of your cost function, you can use, instead of truncational singular value decomposition or SGAT, principal component analysis, principal orthogonal decomposition, whatever, instead of using that, you can use an autoencoder. So encoder and decoder neural networks in order to compress the space, solve the data assimilation in the latent space of the neural network, and then go back to the physical space using a decoder. When I say that, I mean that so for classical data assimilation, we usually say that we are solving data assimilation in a control space. When you want to translate that in machine learning, in a machine learning vocabulary, you have to say that you are solving in a latent space, as always is there of vocabulary sometimes. So, but let's see how it works. So this is work I've done with one of my students, and we published that last year. And as you can see from the table on the left, we have to notice two things. First of all, that as expected, mean square error is reduced. And of course, you can expect that because, as I was saying, you are maintaining nonlinearities. For the one of you which are interested in going deeper in the details, Julian proved in this paper that the results provided by this technology are exactly the same provided by. So we are still keeping, you know, a good quality, good level of accuracy as we do for the control space, and the execution time, as you can imagine, we are gaining like also 1 order of magnitude of execution time in terms of. So we are comparable of PCA, but with the PCA we reduce the space quite a lot. As I was saying, in the previous model, we were like fixing a time step. So we had a fixed time step and implementing a 3D data assimilation. In particular, it was a 3D VAR. But what if we want to implement a fourth-dimensional data assimilation approach? Can we do that in a latent space of a recurrent neural network? Answer, yes, we did it. We did it, and we have done that with another student, Maddalena, the past year. We submitted this paper. So actually, this is how it works, how the architecture works. So you have, same as before, reduction of the space. Then you have these LSTM, which is, as you can see in the figure on the right, is a recurrent neural network. So it's a neural network which is optimized to train temporal sequences. And then this is, let's say, your surrogate model in your 4D data simulation. In particular, we implemented here like a Kalman filter. So we have like this integration of the observations in a loop, as shown in this prediction correction loop, where L, in our case, is not the forecasting model, the CFD anymore, but is the surrogate model. And same, all these matrices of the Kalman filter, of the correction in the Kalman filter, are computed in this latent space, in this small space. But let's see how it works. Still a pollution, as I said, but this is for indoor analysis. So we had like a room in South London in a building with 7 sensors, and then the CFD always implemented by Fluidity. These are, for example, images of few time steps. What happened when you open the window and the fresh air, fresh in London, not so fresh, but let's say more fresh here, come into the room. And we try to integrate that. So we build the surrogate models for the CFD, and we integrated data from sensors. So as you can see in the table on the top, we have what happens then when you go back. So what happens in the physical space? So it's not these values of mean square error are not in the latent space, so in the control space, but is when you go back. And when you go back, as you can see, you have like a quite good improvement in terms of both accuracy and efficiency if you compare the table on top and the table on the bottom. You can see that the mean square error is improving the accuracy of up to 3 orders of magnitude, and the same is for the execution time. So we are quite happy with these results. However, all these, standard, this is like, let's say, a standard data simulation, standard use of data simulation that we were like just, improving somehow in terms of efficiency, in terms of accuracy, trying to have benefit from what a neural network, what a machine learning model can provide. However, some other kind of questions, sometimes more interesting, will be, what about if I don't have information from observations all the time? And for some applications, it's not so a problem because especially the applications using data from satellites, they have more continuity. But for us, we cannot have sensors all the time collecting for air pollution, collecting data in the city or in the train station, and also for other kind of problems. For example, medical application, we cannot have monitors on people all the time. So another important question for us was, what when I don't have information about the observation, can I still use what I had, the benefit I had from data simulation to improve somehow the quality of the results of my CFD? The answer was yes. So what we have done, the idea is quite easy. And you can find more details in these papers that we have published about the integration of deep learning with data simulation in a classical space and in a reduced order model. But the idea is very easy. So it's like you run your CFD, and then you have your data assimilation, because you have observation, you have your data assimilation. Then you have a misfit, but not the classical misfit that we usually consider in data assimilation, where the misfit is between CFD and observations. No, in this case, the misfit is between the CFD and the data assimilation. What I mean? I mean that we are assuming that the data assimilation is like the ground truth in our case. Obviously, because the observation that we have for our application most of the time are affected by an error. So data assimilation helps us to also to balance this error between observations and CFD. This is the reason why we use the data assimilation as like the ground truth. We compute this misfit between the CFD and the data assimilation, and then again, and then again, and then again for a temporal sequence. Then we train a neural network with this misfit. And then we use this network that we trained, we couple the network with this M, where M is our CFD. Okay, but let's see what happens if I do that. If I do that, I have the results that you can see on the right-hand side. So we have, let's say, the CFD and the observations on the left top images. On the bottom, it is what I have with a standard data assimilation. So assuming that I have that information and I assimilate that. And on the bottom right, there is the result of these deep data assimilation. In this case, reduced order deep data assimilation. You have to consider that the results of this RODA, of this deep data assimilation, are obtained without any information about the observation from the red line. So we train the network, then starting from this red line in the graph on the right hand side, we started forecasting. So the green line is a standard data assimilation. So for that one, we are assuming we have the observation. For the blue one, we are not assuming we have observations anymore, but it is still able to follow what a standard data assimilation will say to you. So, and the benefit is not just that one, it's also that obviously as a neural network, it's quite after the training part, it is very fast. So we are going like, we are talking about 1,000 times faster than a standard data assimilation. Still talking about the surrogate models. And why we want to have the surrogate models is, as I was saying, because in data assimilation, we want to, especially in the 4-dimensional data assimilation, we need to integrate somehow the model in it. But if we want to integrate this model, then instead of a toy model, we want to use a surrogate model. It means that it has to be accurate. This is the reason why we develop quite a few different technologies based on the adversarial network and recurrent neural network, coupling adversarial approach with recurrent neural networks. And these, on the right-hand side, there are like a few examples of, in the middle, there is our first surrogate model, and we were already impressed that at least 2-3 time steps it was able to predict. But now, I'm not showing that today, but today, before this meeting, I had a meeting with one of the postdocs of the data learning group, and now we are able to run for 80, 90 time steps without necessity of assimilating new results, because it's starting to be very, very stable. And you have to consider that all these is trained on a structured meshes, so it's like not so standard approach to train the networks, because the data are not structured as usually machine learning are able to work with. And also in this case, the forecast is 10,000 times faster than the CFD simulation. Other kind of surrogate models, I will go fast on this because I want to show you something else, are based as I was saying, on generative adversarial networks. Also, and with the generative adversarial networks, you can also build, let's say, that latent space. I was saying the control space. So you can reduce everything in a latent space, in a control space, if you want to use a different vocabulary. And then in that space, you can do both data assimilation and surrogate model. And these are the first results. On the top is what happens when you, as I was saying, also data assimilation helps us to improve the stability of the machine learning. On the top is this first version of GAN without data assimilation, and on the bottom is with data assimilation. As you can see, the patchy stuff that you see on top are completely disappeared. And you have to consider that this simulation to run on a standard machine as it was running, it takes like 172 seconds, and the reduce order takes just a few seconds, so 0.25 to 0.3 seconds for pressure for tracers and for the velocity field. Obviously, the velocity field is a three-dimensional field, so it takes just a bit longer. Other question. Okay, we understood. We can use this combination of machine learning, data assimilation to build this surrogate model, so we can have our computational fluidodynamics software running faster. So we have these emulators running faster. Good. Okay, but what if we don't have the CFD? So can we still use these kind of models to simulate something that the model didn't see before? For example, just to give you an example, this is a bus stop, and this is in a 3D canyon. So all the simulation I'm showing you, obviously I'm showing just slides to show the image, but they are three-dimensional and with abstracted meshes. So this is, for example, in a 3D canyon. And what is happening? The bus is coming, then it stops, then it starts again, etc. So after a few time steps, the particles are going to on the floor. Okay, but what if I want to build this AI model completely on machine learning and data assimilation to simulate, for example, two buses crossing? In most of the streets here in London, we have big roads with two buses crossing. So can we simulate something like that? So this is what we implemented for trying to answer this question. And this is like a combination, as always, of convolutional autoencoders plus recurrent neural network plus data assimilation to ingest new information, for example, from sensors located at the bus stop. And so we were happy about the accuracy, but what we were really impressed it was about the efficiency, because we can run these with two bus stops just in 1.2 seconds for one epoch. And for the same like one time steps, the CFD takes 998 seconds. It means that if you want to simulate something like that for all the bus stops in London or in a big city anyway, in Rome, whatever, you cannot really do that with a CFD. It starts to be computationally too expensive. But with the AI models, so with machine learning and data assimilation models, able to ingest new information, you can do that in with the again in terms of an efficiency of 3 orders of magnitude. Okay, everything is beauty, but we were saying at the beginning, yeah, but you were saying about dimensionality constraints. For the one of you working on neural networks, you know that this starts to be like computationally very demanding. So when we have very big domains, then we introduce domain decomposition. The domain decomposition in this slide, as you can see, is like strange, no? It's like it's not structured, but obviously because as we don't have structured grids, we have to adjust the domain decomposition to the unstructured grid. But it works like quite well. Now, just to go toward the end of the presentation, all the models that I was like showing you are like coupling data assimilation and machine learning, let's say in a sort of algorithm level of the math stack. And I grew up during my PhD, let's say 11, 12 years ago, with this sentence about the point that adapting new programs to fit new machines was like means adapting the new programs to work as the old one. The new machines to work as the old one. And I exactly translated, let's say, that for data scientists. So where the main point is that if you try to adapt the old algorithms for data science to the new data that we have, and is huge what we have now, you are just trying to use the new data as the old ones. So it doesn't really make sense sometimes, no? So this is the reason why we are also working on high level of the math stack, on the introduction of completely new ideas of assimilating data, completely based on neural networks. So we don't want to minimize a cost function anymore. Let's see if we can do that just with neural networks, if it can be done. So this is the reason why we developed this neural network called neural assimilation. It does what the data assimilation do, but it is completely on a neural network, or better, is a two neural networks coupled. One which is trained on the forecasting data, another one which is trained on the observations. But the main point of this neural network is that the neural networks are coupled so that they share information about the hidden layers. I will not give you too much details about that. If you're interested, we have a paper about that. But to implement that, we use long short-term memory for a few reasons. The main point is that the long short-term memory, which is a recurrent neural network, is very easy to couple. So it was like very good for the first experiments. And then also because LSTM is very good in learning temporal sequences, as I said you earlier. We tried to apply that starting from something simple, not simple, but one-dimensional. So oxygen diffusion across the blood-brain barrier. And we had quite few good results because we were able to have this neural network producing the same results of a standard gamma filter, as you can see here, but instead of running in 138 seconds, we were running just in 0.11 seconds. Okay, you will say, yeah, but you have to train it. So when after I train it, I have new information, I have to retrain it, is useless, no? No, because the way we train our neural networks is including information, new information, implementing a fine-tuning approach. So you don't have to retrain the network from scratch, you have just to adjust the network. So I will go fast here. So this is the same, but implemented to air pollution in a room. So same test case I was showing you early. So 7 sensors and the CFD simulation provided by the software Fluidity. And we have that using this neural assimilation, and we compare that with the results of the optimal interpolation. As you can see, in terms of accuracy, we have almost same order of magnitude for the error, so 0.59 to 0.60, and on the right-hand side, 0.54. So more or less, we are having the same results, let's say. But in terms of efficiency, the optimal interpolation takes 267 seconds per time step, and the neural assimilation takes 0.03 for if you couple that with the PCA, and 0.01, 14, let's say 15, if you work with an autoencoder. The difference between PCA and autoencoder here is just that we use or PCA or autoencoders to reduce the space. But the recurrent neural networks to train the neural assimilation is exactly the same as for the blood-brain barrier. last thing, I was mentioning you at the beginning, optimal sensor placement. So when you have information from a lot of different data and you just want to capture the optimal one, you can use models based on Gaussian processes and data assimilation. So still data assimilation and machine learning together. But in this case, it's to place the sensor in the optimal placement. As you can see in this red box, using these optimal sensor placement, we can maintain the mean of the whole distribution quite perfectly. And also, if you see on the right hand side, in terms of error, we can reduce the error of 1 order of magnitude with respect to what we can do using just random placement in the city. Same with indoor placement. We can have, if we just assimilate data with random sensor placed in a room, like in a random way, we have an impact in the data assimilation of, so we have a 2 orders of magnitude of improvement. So instead of 0.17, we have 0.023. But if we use the optimal placement, we have 0.0005. So which means that we are really strongly improving the accuracy of the CFD if we assimilate data from optimal placement. I just want to leave you saying that if you, all these models I was showing and all the codes are available. So in case you are happy to download our codes, to use the codes, you are very welcome to send us an email and we will show that with you. Also, we have few events coming. One is this year is the 3rd edition that we have a workshop for the International Conference on Computational Science. The workshop is on machine learning and data assimilation for dynamical systems. The call for paper is closed. Now we are in the process of reviewing the papers, but you are still in time if you want to attend to the meeting, hopefully in person, who knows. And to leave, just as a quote to the future data scientists, especially the young students starting working now on data assimilation and or machine learning or data learning together, is that the imagination, as Albert Einstein was saying, is the key here. And this is just a post that has been posted by University of Reading from me now 3 years ago, where I was saying, imagine a world where it is possible to accurately predict the weather, climate storm, tsunami, and other computationally intensive problems in real time from your laptop and even mobile phone, etc., etc. So the point is that this is probably a key component. The couple of machine learning with data assimilation is probably a key component of future numerical forecasting systems. So hopefully a lot of new data scientists, novel students will join us in this, trying to make it real. And thank you very much.
Thank you so much, Rossella. This is most fascinating and inspiring lecture, certainly for me, but I guess also from the others. I go directly to the questions because we already have a few. More are added, so I want people to get satisfaction in getting your answers. So the first question, which is very interesting, is how can we be able to detect low quality data from the early stages? Can we, yes, any suggestion?
So
low quality data.
Yeah. So low quality data, it depends if you have already the data set or if you have to build the data set. So if you have to, so low quality data means when you have, for example, you want information about the temperature, but you have values of pressure. So this is what I mean with low quality data. But probably what the question was about is how to capture when you don't have the good data. So it is the few approaches can be applied from scratch, from the beginning. So the first one is using the technologies I was showing at the end. So optimal sensor, optimal data selections, because I was showing you the application of these methodologies for the optimal sensor placement. But actually, imagine you have a bunch of data and you want to just capture the data which are more meaningful for you. You can run these software, which are basic models on mutual maximizing the entropy, mutual information. They are based on Gaussian processes with data assimilation. And using that, the software gives you just a subset of your data, which are the high quality in terms of meaning for you. If you don't have your data set yet, but you want to build the data set. So for example, if you don't have sensors, but you want to understand where you have to place the sensors, then you also can build, can use this kind of model, but the input of the model will be not your database anymore because you don't have the database yet. But what we have done, which is like innovative and can be useful for people that don't know how to collect data yet, you can use data from your CFD. So somehow the model, this optimal data selection model, can capture from your CFD data where is the most higher variability so that you can, for example, collect data in that locations.
Yeah. So thank you so much. This is kind of exhaustive. And the next one is your neural networks help to deal with nonlinear features. Could we use neural networks to avoid the normality assumptions of the errors?
Yes. This is exactly why we started introducing the neural networks. So when you, for example, when you build your background covariance matrix, sometimes you don't even build that. You build a sort of deviance and then you truncate that, etc. So with convolutional autoencoders, which is the kind of neural networks that we use, you are able to build directly from the data a reduced version of your background error covariance matrix, which is where the main point comes. No. Second, also for the H function, because another point in data assimilation is a linearization of the observation function. Also, in that case, you can use a neural network to build the H function and then use that function built completely with the neural network in your data assimilation. And in this way, you can, I probably show you a slide about that, but you have a good benefit in terms of accuracy, because you are not introducing so much approximations.
Yeah. So, for example, going back to the question, when you were talking about the low quality data, and we're talking also about an observational operator that was translating the measurement that you have into the fundamental quantity that you want to improve. Here then also will be, so that the question of low quality is connected to the observational operator that might be very difficult. But in the real world, when you talk about large scale flow field, data are collected whenever they can and for whatever measure kind of, you cannot decide, because when you have to do weather forecasts, you have the globe. So you have to have in China, in Australia, in Canada, in Europe, taking measurements with a standard. And normally the quantity that is measured is not low quality. We don't call it low quality. It's more kind of is not the quantity that you would like to choose to train your data assimilation system, right? So it's always a question of observational operator, but you're giving a very nice perspective, which is very revealing, using the neural network to form the observational operator in your data simulation. That's a very nice. Have you shown an example of this?
Yes, if I can go back, probably it's easier if I do ask and I go. It is quite at the beginning here. So yeah, so here we also train the observation operator. Okay,
excellent. Thank you very much. So let me go to the others. So we have now Ali Aidogdu from CMCC who asked, thank you for the conversation, and it's talking about another topic. Is your adaptive mesh really fluid or is it fixed in time?
No, it's fixed in time.
It's fixed in time, okay, because we know Imperial College, you know, so we know the passion for non-stable. Okay, so it's fixed in time.
This is, if I can conclude, these experiments are with fixed in time. But what we are implementing now, there is a postdoc working in the HINAIL project, Cesar. It's also working on, you know, the ability of the network to train the adaptive mesh when it's not fixed in time. So it's adaptive, fixed now in the experiments that I was showing. Sure. But what we are doing now is also changing the mesh in time, because obviously they are like they don't want to fix the mesh. So as you were saying, they are not happy when we have to fix the mesh. So
no, I know. So and Ali was asking you, can you tell us what are the drawbacks? I mean, are there, you know, some immediate thoughts on what would be a sort of a ambush situation where you cannot really use your methodology developed up to now, when the grid is unstructured and not fixed in time?
Yeah, but you know what? I will say where this technology cannot be used for that yet. But this is the beauty, you know, of being researchers and scientists. It's like we know what it can be done. It's just a matter, you know, of working on that. So, for example, now we don't have a neural network which is able to train in time an adaptive mesh, but also we change at each time step, but it can be implemented.
Thank you. This is great. I like the philosophy for sure. So then there is another question that says, almost all the models you have presented require the choice of several hyperparameters, likely affecting in a significant way each model performance. What strategy do we adopt to define the optimal hyperparameter configuration?
So there are optimization functions that you can use for optimizing the parameters. So we use the optimization functions. In our backpropagation, we also try to optimize the hyperparameters.
Okay. So thank you so much. We have also, have you tested strategies like dropout during both training and prediction to forecast confidence intervals?
Not with data assimilation, just in the surrogate models, because the surrogate models come with an uncertainty in it. And not for the data assimilation side. So, for example, this kind of models here, I'm not showing you the image here, but so, for example, if I show you what is behind this graph, you can see So it comes out with an uncertainty in that, but this is not with data assimilation, it's just the surrogate model.
Okay, so thank you again. So I have another question here. Since we are using neural network deep learning in the adaptation of data learning, what happened to the hyperparameter of the neural network model during the cycle of training?
Yeah, beautiful question, because this is, so the one way to use data assimilation is to set up the hyperparameters. What I was saying on the first slide about explainable AI, so use data assimilation to set up the hyperparameters of a neural network. And yeah, this is, I think this is our approach now. I think this will be quite popular. If you check online Bayesian approaches for explainable AI, you will see what I mean. Data assimilation is a Bayesian approach somehow, no? Yes. So you can see how the hyperparameters can be even more explained introducing the data assimilation in the neural network.
Thank you. I forgot one question before. Is there a limit on data points that these methods have been tested with? Have you tested in large models?
Yes, but so this is, for example, let's say 15 millions of nodes. The complexity is quite high of the model, so it's a quite big problem. We are cheating here because we are also introducing domain decomposition.
Okay, no, it's not cheating, domain decomposition.
No, I mean, it's not like training a network on 15 millions of nodes. It's like, you know.
Sure, it's being intelligent to train exactly on a 13 millions of nodes, because it's clear that we have a finite speed of propagation of information. We're not relativistic here. Andrea Cipollone, also from CMCC, thank you for your presentation. Do you need to create a neural network for the adjoint of observational operator too?
Yes.
Yeah.
Yes. The group working, we collaborate a lot at Imperial, call that sensitivity map. No, I don't know why instead of just a joint, but it's like an adjoint build using a neural network.
No, but we use it also in
okay.
Physical fluid dynamics. Yes, we call it when we do the adjoint to find out what was the primary source of a response. We do the adjoint, we do a sensitivity, we call it sensitivity. Okay, so then have you done data immutation for missing data? Immutation. Federica Zennaro, have you done immutation? Oh, imputation. Sorry, this is me. I'm reading. Okay.
So you mean, but you know, we use data assimilation in real world scenarios. We use data assimilation to fill the gaps, no? Sometimes, yeah. So yeah, this is how we fill the gaps.
Excellent. So I have one question. So this is of extreme importance to use, you know, for urban meteorology, to use your approach, because we know how important is urban meteorology for the future. But you know how, you know, somehow when you treat this problem, it's a bit less nonlinear. Because we have so many buildings and the flow field. I agree, you showed the flow that was going toward. When you are really in the free atmosphere or the free ocean, by the way, you forgot to put the ocean among your dreams. But how are these results getting to that efficiency and that quality? Are they, you think? When the flow field is fully nonlinear and you have eddies interacting, exchanging energy.
Yeah. Actually, you know, Thursday is the day I have meetings about air pollution. So I just left a meeting 1 hour ago about that. And let me see if it is shown, probably not in this graph, but you see in this slide, this surrogate model. So we are able, in the part of when you try just to predict using neural network, so you don't have the CFD anymore, the neural network is also able to predict the creation of eddies, new one. So,
okay.
So yeah.
No, fine. It's a specific process of creation of eddies, this behind an obstacle, but that's okay, fine, I understand. And as you're saying, we have to look for something also in the future, and we haven't finished to do. Most interesting, I was looking if there are other questions. Okay, if not, well, just to tell you that we almost had 200 participants at a certain, during your talk. We have less now, but I would like to thank you for your seminar, very illuminating, and we hope to see you soon.
Thank you, hopefully in person. Thank you again for inviting me. Have a lovely day.
Bye-bye, everybody.
Bye.
Bye.